Hi, now let's start. Today we are going to introduce those famous pre-trained models. We will start from the question why we need pre-training. Normally, when a new task comes, we need to train a new model. The drawbacks are it is computation expensive, time consuming, and it also requires a lot of storage space and annotated data. There has been some solution like model compression, acceleration, feature learning, which aims to solve these problems. But the straightforward question is whether we could do transfer learning. So when a new task comes, they can only fine-tune part of the model with low data cost. The goals for computer vision language modeling is similar. The only difference is that their data modalities are different, which leads to the difference in how their features are extracted. It has already been widely applied. We know that PyTorch has absorbed many pre-trained models for computer vision, like VGG family, ResNet family, Inception family, MobileNet family, and so on. These pre-trained models have already been developed and open to public from 2012, as the competition in the ImageNet gained momentum. From language modeling, the emergence of models like BERT in 2018 has significantly impacted natural language processing tasks. These models included here are the many models we will introduce today. These models began to emerge around 2019. That was a promising year of NLP. The next question is where we can start from. You know that there are many tasks in NLP. Here we provide a quick review on these tasks. The first task is the constituency parsing. The goal of this task is to understand the text. It analyzes the structure and syntax of the text, breaking sentences into tree-like structures to determine the dependency relationships between words. Its downstream applications include machine translation and question answering systems. The goal of machine translation is to automatically translate text from one language to another. The input is the source language text that needs to be translated, and the output data is the translated text in the target language. And the third task is the question answering. Even though there are many kinds of methods for question answering, the goal of question answering is to generate relevant answers to user queries based on a given context or a set of documents. The input is a question or query and plus a context, and then it will retrieve a set of documents which contains information that relevant to the query. And the output is the generated answer to the question. Now, we came about the problem that if we need to train a pre-training model for a general language, we need to train it on massive amount of data. However, many of these tasks are unsupervised tasks, which requires extensive manual annotation, much like an ImageNet. Nevertheless, language data inherently possesses semantic information coherence. Can we leverage these features to train an unsupervised training model? Now the researchers come out a task named the next word prediction. The input of model is a sequence of text. Then they goes into the word embedding layer. It maps each word in the input text to a dense vector representation. Each word has a corresponding word embedding vector, which captures the semantics and contextual information of the word. Then they input the embedding vector into RNN or transformer, then predicts the next word by learning patterns and context. The model's output is a probability distribution, which represents the likelihood of each possible next word occurring in a given context. The most common next word will have the highest probability in this probability distribution. The next word prediction is inherently an unsupervised task. Now coming to the word embedding layer. The goal of word embedding is to map words from discrete symbolic to a continuous vector space. It aims to capture the semantic information on contextual relationships of words so that similar words in the vector space have similar vector representation. There are two traditional word embedding methods, continuous bag of words and skip-gram. The SIBO's goal is to predict the target word based on the surrounding words in the context. The input consists of the surrounding words within a fixed size context window, typically a few words, and the output is the target word. The SIBO employs a shallow feed-forward neural network architecture. The input is the average of the word embedding vectors of the context words, which is then passed through a hidden layer to predict the target word. The skip Grams model's objective is to predict the surrounding words in the context based on the target word. The is the target word, and the output consists of the surrounding words. And the skip gram uses a neural network architecture opposite to the SIBO. It maps the input to multiple outputs through a hidden layer. Global vectors for word representation's main goal is to learn word vector representation based on global vocabulary statistics. It constructs a vocabulary co-occurrence matrix with a context window and then learn the semantic relationships between words. Now we see another problem. The word embedding vectors typically obtained from word-to-vec and globe are static word embeddings, and they are one-to-one projection, meaning each word has a fixed vector representation without considering context. That means the usage of the learned embedding model is we can retrieve the embedding for each word when we call the embedding layer. But the problem is many words have polysemy issues. A single word can have different meanings in different sentences. For example, in the case of the words python and pandas, they can both represent the PYPI leaves and also refer to a kind of animal. The way to solve this problem is the contextualized word embedding. The primary goal of contextualized word embedding is to capture the semantic variations and polysemy of words in different contexts. The model uses all preceding words of the target word to predict the target word. And intuition comes out. Why do we not incorporate red content into input to predict the target word? By incorporating more information in this manner, we can potentially enhance prediction accuracy. However, it's crucial to be mindful of two important points. The first concern is the issue of data leakage. We cannot include the predicted word as input. The second is the sequence structure. We cannot mess it as the sequence order is important and contains some information. So researchers developed bidirectional language models to solve this problem. Here, the architecture is a little different from BERT. It consists of left to right and right to left two modules, not the same as BERT consists of one whole module. ELMO is the abbreviation of embeddings from language model. The bidirectional language model is the foundation for ELMO. The input is sequence of tokens. The language model learns to predict the probability of next token given the history. In the forward pass, the history contains words before the target token. In the backward pass, the history contains words after the target token. The predictions in both directions are modeled by multilayer LSTMs with hidden states. Then these two kinds of hidden states goes into the softmax normalization. The output of softmax layer is the probabilities of word prediction. The model is trained to minimize the negative log likelihood, which means to maximize the log likelihood for true words in both directions. Here, the parameters stands for LSTM, embedding layers, and softmax layers. We still have a question. If we train on a supervised task, how it catches the representation, and will these features be effective enough for the downstream tasks? So let's check the representation catched by Elmo training. In Elmo, different layers of BILM produces different hidden states, each containing different types of information about the task. To utilize this information for downstream specific tasks, Elmo learns a task-specific linear combination that aggregates all layers of the hidden states. Here, gamma and S are hyperparameters learned during downstream task fine-tuning. Gamma is a scaling vector, which is introduced to correct the mismatch between the distribution of LLM's hidden states and the distribution of task-specific representations. S is the linear coefficient learned for each end task and normalized by the softmax to keep the constraint as sum to 1. The hidden representation learned by top layer in BiLN module contains much better representation for semantic tasks. This task emphasizes the meaning of a word given the context. The one learned by first layer is better for syntax task. It infers the grammatical uh, role of a word in one sentence. Good news is that after proving the capability of Elmo, their researchers can stack information from different layers together to help to improve variety of NLP tasks. Then the question is, we have obtained the model, then how to apply to the downstream task. Take those output embeddings and feed them into whatever architecture you want to use for a specific task. This is the first choice. And the second choice is that one can update weights for their downstream specific network, but keep the Elmo's parameters frozen. The third one is that it depends on the performance. If the performance is not good, then one might choose to fine-tune the whole model. Here we can see massive improvements across 6 benchmarks datasets. The question answering, and textual intelligence, and so on. We now answer the question whether it solves the core problem of polyphony. Let's take a look at the contrasting examples provided in the paper. If we were to use the original glove word embeddings, it based solely on the words embedding in space, we would get many synonyms, not only including the polyphony of play, but also varieties of installations of play. However, if we were to use Elmo, it would search for semantically similar meanings of play based on the context. For example, if it refers to the sports game or stage performance, Elmo would only find the play with same meaning. However, Elmo contains some drawbacks. It utilises LSTM instead of transformer. It has been claimed that the transformer has better feature extraction capability than LSTM. At that time, transformer was actually proposed. So someone claimed that if Elmo used transformer instead of the LSTM, it would might achieve better performance. The next question is that is Elmo enough as a pre-trained model? Whether we just stick to Elmo as pre-trained model and leave the improving place for downstream tasks and their model training. So why we still pursue pre-training models? This is an image from the super glue paper. The main point of this image is to illustrate how much large language models underperform compared to humans on the glue dataset. Glue dataset is a benchmark. It collects all diverse natural language understanding tasks. These tasks are used to evaluate the performance of NLP models. These tasks include the tasks we just mentioned for Elmo, sentiment classification, text matching, question pairing matching, and so on. Each task has its own training and testing set, so researchers can compare the diverse capability of their models. Here, each column stands for pre-trained language model. Each point stands for the performance on this model on one specific task. And the blue dotted line is the average of these 9 tasks, while the black line stands for the human performance. So the answer of our question is the initial Elmo model is far from reaching the level of human understanding of language tasks. This is why researchers need to continue their efforts in pre-training language models at the We know that there are two RNAs. The first one, developed by Baidu, is enhanced representation through knowledge integration. Then inside is the random masking in BERT good enough? We know that there exist some phrases where several words together represent meaning. The strategy of random masking can disrupt the integrity of phrases or word combinations. Another problem is the generalization capability. For example, previous the model only see the Apple Watch. Now, as Apple has released Apple Vision Pro, can the model recognize it as a product of Apple? Or it can generate embedding stands for these phrases, so that the embedding closest to other Apple products in embedding space. So they proposed whole word masking, intent to mask entire words as units to maintain the integrity. Then the first question is, to which level they need to mask? There are two levels, phrase level and entity level. For example, in phrase level, it will mask something like a series of. They will mask a proportion of phrases in a sentence. In entity level, it will mask J.K. Rowling. So they will mask out some name entities such as personal names, organization names, product names. Comparing to basic level, the basic level randomly masks out one Chinese character in each word. Then more questions generated. Firstly, since this is an unsupervised learning, how did they recognize the entity and phrases to mask? What we concern is whether they include other supervised information, whether they need extra annotation. They use the automatic part-of-speech tagging tool and name entity recognition tool like spacing NLTK, stand for NLP, to identify the phrases and entity, so they can avoid human annotation. The second question is, what is the relation between two levels? The answer is, these three levels are masked sequentially. First masked in basic level, then entity level, and then phrase level. So the final masked input includes all kinds of masks. Lastly, how did they label the output? Since it is contextual learning, the continuous mask of words won't affect training pipeline. The input-output format is just the same as BERT. For the architecture, ERNIE used multi-layer transformer as a basic encoder, just like what GPT and BERT did. ERNIE also incorporates conversation data into its training data, primarily focusing on two aspects: reference relationships and semantic consistency. The motivation here is, for example, if we mask the words in the red line and only train on the last two sentences, we won't know they present for laptops. We also don't know what user is picking and buying. If just give last two sentences to the model and fill in the blanks, it may directly output to buy a computer. Let's check the performance. It shows that it improves a little bit on these NLP tasks comparing to BERT. Mainly these tasks are for cross-lingual because in Chinese they always use multiple words. We just take a glance because this paper is not our target. This paper just had the same abbreviation with another earning. Now we consider another problem. That for most current pre-training large language models, they require a lot of computation resources. How can we reduce the cost? As we have mentioned, others might think about the data perspective, use future learning, or mode perspective, like model compression. But currently, we are working on pre-trained large language model. We cannot consider trade-off between performance and time consumption. We cannot sacrifice the performance. So some researchers think that whether they can change the task, as the sequence generation task is quite time consuming, whether they can change the original sequence prediction to a binary classification task. This binary signal is whether this token has been replaced or changed. For example, here two words are masked, and one is another is ate. It means that the chief might first cook the meal, then ate it. So ate is a word that might be substituted. Then a question comes out that whether this design is reasonable, whether a model trained on discrimination task can substitute the sequence-to-sequence pre-trained model. The answer is that it is somewhat reasonable. The discrimination task also requires the model to capture the grammatical, semantic information in the given sentence. For example, the difference between these two sentences is the verb. So this word is of highly flexibility to be other words for the given context. But for the word the, it is of common usage to be used before a noun. So it is unlikely to be replaced. So the language model needs to know how the words work here. Then it can distinguish whether the word here is of highly flexibility. Another perspective is that it is more like a side effect. The language model can learn whether the word is not only the flexibility, but also of correct usage here. So it can be handle the error and typos in some sentences inputted by the user. Then we face a problem that again this is an unsupervised learning. How can we generate the data without annotation? The most straightforward method is to randomly sampling other words in corpus to substitute the target word. But if we apply this method, then the negative sample we obtained is not distinguishable. It is meaningless. Again, our target is to train a large language model which can represent meaningful information from sentences. We also need to train a powerful discrimination model. So we need to generate reasonable sequence data here. Then what is the simplest method for this sequence generation task? These researchers think about using a small bird to generate a sequence based on the mask sentence. So this is the lowest cost method to produce most distinguishable pair. There are several problems also came up. Whether it improves comparing to a single small bird, since it already trained on a pre-trained model. If it just improves a little bit, then the total computation cost will also surpass most training models. Then it is not reasonable. And the small question is that whether they will fine-tune a small bird or just frozen the small bird. The answer is yes, that they will fine-tune the model, but in a way to save the floating point operation. So in order to compare the benchmark fairly, they would compare the performance on glue dataset with same floating point operations. We will check this later in the performance part. Another question is that as the output of this model is binary signal, then how to apply this model for downstream tasks? So regardless of its training, we first assume it already possesses most of capabilities of a language model in this part. The output is a probability vector. It can be regarded as embedding output, so it just needs to pass the output to another module and to be fine-tuned by adding another module, maybe a small neural network. For classification tasks, typically, one or more fully connected layers are added on top of the electron model. And for sequence labeling tasks, it might involve adding a classification layer on the top of output for each token to predict labels. The design here is it randomly samples key position from inputs to be masked. Then these masked tokens are predicted by a small bird. denoted as the generator. Then the discriminator trains on a binary classification task. The label is whether the target word is replaced or not. The architecture of discriminator is as bird. The difference with get and GAN here is since the word is masked and discrete here, so the gradient of discriminator cannot be passed to the generator, a little similar to ReLU. So as they are not connected, they can only set the loss target of generator is the still same as bird. The loss of generator is a negative log likelihood, just as same in other large language models. The loss of the discriminator is the cross entropy because it is classification task. Then they are trained at the same time as a linear combination. Then let's compare Electra to GAN. Electra is quite different with GAN if even they have similar architecture. The input of Electra is the real text, not noise, and the output is real text, not fake. And its generator not aims to deceive the discriminator. From the gradient's perspective, it cannot flow from the discriminator to the generator. The alternate, and thus they considered whether performance could be improved by sharing weights with the discriminator. After all, the discriminator is only trained on a simple binary classification task, so the training might be a little difficult. During their trials, this method can help. Here they just put some metrics in paper, didn't visualize it. The second considering is, based on their architecture and task, what is the smallest bird that can possess the most fundamental capabilities? So they try to reduce the layers and check the performance. Here, the X label in image is the size of generator, and the Y label is the glue performance. The conclusion from author is, the performance is best when the size of generator is half or 25% of the discriminator, comparing to other ratio setting between generator and discriminator. The insight here is a strong generator will also enhance the difficulty of discriminator training. The third one is the gradient issue. The author used other laws together with some tricks to pass the gradients from discriminator to the generator. Here, the figure shows that the original Electra outperforms the one adding other tricks, so we won't go into details. Another trick is that they try to train generator first, then freeze it in the first phase, and initialize the weights in discriminator weights by generator weights in the second phase. Then they train discriminator in same steps. Then let's check the performance. The left one is the zoom out version of the one on the left, right. On the vertical axis, we have the glue scores, and on the horizontal axis, we are measuring floating points operations. The conclusion is that Electra always outperforms BERT with the same flowing points. The goal here is to check whether Electra enhances pre-training efficiency. Here the metrics are training and inference, floating point operations counts, and the number of parameters. The speed up is computed based on the float. In order to train on a single GPU, the author creates Electra Small with BERT Small as the base model. Then they compare it to Elmo GPT and BERT. The conclusion is, no matter under 14 million parameters or 110 million parameters, under the same level of parameters, Electra always outperforms BERT. Then the author also checked how about the performance of the larger Electra to compare with Robetta. Here the metrics are floating points. We can see that on the same level of floating points operations, the Electra always outperform Robetta in multiple tasks. Here is another enhanced language representation with informative entities. Another insight is whether we can incorporate structured entity information into the ERNIE. For example, Here the person has two identities, the songwriter and the writer. So the relation between this person name entity with different items are different. We also want to incorporate this relation in the model. Or we want this additional information can help part of NLP tasks, like relationship. Here the input is text and the entity with relations. The architecture consists of two parts. The input of first part is only the sentence, and the input of second part is the embedding output of first module and the entity embedding. Here our concern is the task. They prepare an entity relation prediction task. They randomly mask some token entity alignments, then let model predict all corresponding entities based on aligned tokens. So here partly unknown, partly unmasked. Here another concern is how they merge to get a better embedding output that represents both information. In the second part, both entity and tokens will pass into the multi-head and the attention independently to project them into same embedding space. Then they are merged according to the no-entity alignment relationship, appending to the entity to the first token. Then they go into a fusion layer to fuse. Here, since it is an entity relation classification task, the loss is cross entropy. To apply this model on downstream tasks, the only effort is to modify the input. For common NLP tasks, they just leave the placeholder as blank. And for entity in typing or relation classification, they replace placeholder as special tokens that used for this task. The performance is that Ernie aims to improve those named entity tasks and relation tasks, so it only outperforms BERT in these tasks. Now we consider another problem. BERT is not good at generation tasks because it is trained on whole sentence with masked words. It cannot generate words on partial sequence data like GPT input, so BERT only acts as encoder. For sequence-to-sequence task, it needs pretrained decoder. So the question comes out, how to absorb sequence-to-sequence task into BERT? To answer this question, we first check the elements in different existing language models. So there are multiple kinds of NLP tasks. However, they can be classified as three types of tasks. The bidirectional language model, which BERT includes. And the second one is the left-to-right language modeling. It's totally single direction. The third one is sequence-to-sequence task. During the first sentence, we can see information from right side of the target word as input. But in the second sequence, we can just do single direction prediction. So it contains both part of BERT and GPT. The task is actually decided by its input and output. For Elmo, BERT GPT, the input needs to be masked, and the output or is the probability of wording prediction. So they find that the core of language model is masked. This is also a natural way to unify language models. So the author called it unit LM. Then the problem is from the perspective of mask metrics, whether we can leave the inputs and output as same, but vary the mask metrics to control different tasks. Thus, we can control the network work training by just change this mask metric. From previous description, this mask indicates whether the input can contain which kinds of information, the left side or the right side, or a combination. There are other explorations in this paper to improve the accuracy. So here our concern is the improvement on each task, on all kinds of tasks. Uni-LM performance. Here are the performance of summarization task, extractive QA task, the question and response generation task. Next, we want to check how pre-training helps with the downstream task. This is a figure from paper, visualizing and understanding the effectiveness of BERT. From the figure, we see that if we want to compare the model trained from scratch and the fine-tuned model that trained from pre-trained models, their training gradient curve is totally different. We can see that the fine-tuned model has faster gradient descending at first. And here is another perspective of how pre-training helps. Here are the figures of arrow surveys, which visualize the meanings of voice into 2D or 3D figure. The meaning of this figure is, if the figure is smooth, then it is more generalization capability. We can see that the fine-tuned bird has smaller platform than one trained from scratch. So the model fine-tuned on pre-trained models will have more generalization capability than the one trained from scratch.